I should probably thank organizers first, not just for inviting, but also for planning the schedule in such a way that the talk is like an immediate segue from the previous one. So we talked a bit about building LLM applications. We talked about the tools you can use, the tools that most people use. Today I'm gonna talk about the stuff that is a bit in shadows, hopefully till tomorrow. The open source counterpart of all those cool AI systems. So the talk is titled Bird's Eye View of Open Source AI Infrastructure. And there's been a lot of debate in the last days what exactly open source means in the context of AI. Do we care about where the data comes from? Do we have or do we share the training scripts? And what exactly is infrastructure? I want to dive into LLMs, embeddings, and vector search specifically, talking less about policy. And for now, we'll skip any personal introductions and we'll just jump into the topic. So how many of you are familiar with LangChain? Okay, that's a big part. And how many of you know what Haystack or GPT Cache is? Okay, maybe like 3-4 times less. It's a general trend. So when the web was becoming what it is today, we started getting all those web frameworks like React and Vue and Svelte and a bunch of others. Kind of the same thing is happening now with LLMs. As they enter every single enterprise system, we start developing frameworks that are around them, like how do we use them in broader settings. All of them are kind of similar. The most known one is LangChain. Most of them are written in Python. Some of them are later re-implemented for other programming languages. So LangChain was originally implemented in Python, but it now has a JavaScript version, Golang, and Ruby. And just Python alone is downloaded 5.3 million times a month. So it's a huge base of developers who's already using this. Maybe 2 or 3 of those projects are backed by Microsoft. So it's not surprising to see C# and Java and some of the other like systems languages also present on the list. But for now, we're going to focus on LangChain as the most representative example. So all of them solve the same problem. They link LLMs to all kinds of external services. So we've talked about vector search, we've talked about embedding models, but there are also all kinds of API that have to be linked together. The image that LangChain shared on their website is on the left, but on the right you see something that maybe most of us have seen already, those who use ChatGPT, that you can enable plugins. So in a sense, OpenAI is by itself not only becoming the provider of neural networks, but one of the most used frameworks by itself because they have their own plugins and the ecosystem around them. So the plugins solve a bunch of problems. The most obvious one of them is prompting. It is a form of providing a context to a neural network for problems such as like multi-shot classification. Essentially anything that is not zero shot, and I'll clarify later what it means, but is like single shot or multi-shot requires prompting. So it's not just you explicitly telling the neural network what you want to achieve, but also providing some examples. And a single example is like a single shot system, and multiple examples would be multi-shot. So in this specific case, we have classification maybe of sentiment, like positive and negative. LangChain has become huge in terms of the number of integrations. You can connect it to papers like Archive, to YouTube, to a lot of other systems. It mostly works and is designed to work with textual representations and textual documents. It has about 40 vector storage systems connected, a bunch of LLM APIs, and also open source systems that you can attach to it. And the reason LangChain and many other frameworks exist is because LLMs are not perfect. They have a bunch of problems. And talking about like enterprise applications, the most obvious one is price. So they are charged on per token basis. A token is roughly 0.7 words in length. So 100,000 tokens is 75,000 words. If you want your neural network to summarize all of Wikipedia, just Wikipedia, answering every single one of your questions, This would roughly translate into $400,000 worth of costs, assuming the length of Wikipedia, and I'm just taking the English one. More importantly, they're forgetful, so you cannot shove all of the even English Wikipedia into the context window of a neural network. I think ChatGPT by default uses 4,000 tokens, which is 3,000 words, not too long, so you cannot fit most of the single header libraries out there into ChatGPT's context. The longer version that is available over API, 32,000 tokens, so like 25,000 words. The longest one would be of available commercial APIs Claude with 100,000 tokens. The third problem, also relevant here, is that the networks are trained on public data, so they extrapolate on public knowledge, which may not be enough for most like internal commercial applications, and they're not very good at calling external services. So you need all those frameworks around them to automate the process. When you look under the hood, if you open up the repository, you'll see that most of those projects kind of have identical directory structure. All of them provide retrievers of vector search systems, sometimes split them into separate vector stores, embedding providers, sometimes graph databases for knowledge graph systems, and of course LLMs. The three parts that are most interesting to me would be like closer to infrastructure. In here, of course, you're probably familiar with OpenAI. You're probably familiar with Anthropic, the second most popular system out there, and the contestant, the second best one funded. There are always variants coming from large and like big tech enterprises. Google famously has their Palm system. They're releasing Gemini. There's an open source variant called Llama. Llama and Llama 2 are backed by Meta. Those are great models coming in different sizes. We'll talk more about them today. And sometimes we have like smaller but still large enterprises like Databricks releasing models like Dolly this year, which are open source. And I guess at the time that was the first open source LLM out there. For embeddings, again, you can use commercial services like OpenAI. You can use Cohere, which doesn't provide an LLM, but just provides like exclusively embeddings. Those are quite pricey, almost everything that I've just mentioned. And if you don't want to pay the price, you may want to use models like E5 and MiniLM. So those are open source models that are available in Hugging Face. I was just participating in a hackathon this weekend, and I've built one of the smallest retrieval systems in the past few months, and even that was over 10 million embeddings. You can easily go bankrupt using those APIs if you just like do 10 million embeddings a day. Over this summer, I computed over 100 billion embeddings. So you should probably consider some of the open source alternatives as well. For vector search systems, of course, again, there are commercial systems like Pinecone. There are open source specialized vector search systems and vector databases like Milvus. And there are companies that try to retrofit this functionality into like classical search systems or databases. So Elastic, being a well-known search system, now has a vector search capability, and Redis, being a distributed in-memory key value store, also now provides abstractions for vector search. Part of this is open source. In a broader setting, under different licenses, not always known what data they are trained on, still, some of them are open source. But the question that I keep asking myself every time I see like a major hype cycle, including AI, and I'm part of this hype cycle, is what do I look at when I compare all those technologies? How do I pick the one that it fits my specific use case? And what are the metrics that others can employ? So we're going to start with LLMs, and I'm going to use the model card of Llama 2 as it was released a few months ago by Meta. They've shared it in 3 different sizes. They also describe a few other settings, but again, size is the most important one. So size is the number of neurons in a very loose sense that are being trained inside of this neural network. 70 billion floating point numbers may sound like a lot, especially for optimization problem, but comparing it to some other models, especially like GPT architectures, it's not that much. So GPT-3, I guess, was released a few years ago, maybe 2019. And back then, like 4 years ago, it was 175 billion parameters. Interestingly, like this smaller model that we have this year surpasses GPT-3 in most benchmarks that I've seen. So size is not everything. GPT-4, however, has 1.5 trillion parameters, most likely trained as a mixture of experts. So it's a combination of multiple neural networks gathered together and with a smart router in front of them, aggregating the results between multiple neural networks, likely every one of them being like sub 200 billion parameters in size. So it's about a dozen networks chunked together. The second metric is the context length. So like how many words can we put into a neural network in a single context until we get the answer? The number is not that high. It's just like in thousands of tokens. So you cannot put any book into the context, like a full-blown book. Maybe like in Claude, you can put a smaller book. Most of Russian literature wouldn't fit. So with GPT-4, I guess we can expect some larger context windows soon. But the more important metrics would be not just like how big is the context, but how big was the data set? How much stuff has the neural network seen during its training procedure? In most cases, they will be trained on the same data sets. So the most commonly used data set is called Common Crawl. It's fairly small. It's few hundred terabytes of text sampled from the internet. So it's mostly HTML documents. If you dive into this this data set, and later in the talk, I'll describe how we work with it. I've been working with it for many years now. I store a few copies of it. And what you're gonna see is like it's 52% English, give or take, 6% Russian, and every other language is less and less. So by the time you get to the top 10 language or like top 11th language, you're out of luck, and the language is represented with less than 1% of data in the data set. The second topic that became big this year, has the neural network been tuned for conversations, chat, and more technically instruction tuning? So instruction tuning would be like an additional step in your pre-training pipeline where you teach the neural network how to follow instructions. And the last but not the least, was this neural network fine-tuned for a specific domain, or does it allow you to fine-tune it for your specific use case? So you can take a really large neural network. You may not afford to retrain the whole thing on your data set, which is absurd. You would probably spend millions or tens of millions of dollars, but you can take an existing neural network and tune it for your specific use case. The benchmarks for those things and those neural networks change every day. Like, I haven't prepared this talk until today morning, and generally when I gave talks around AI this year, I really wait till the last moment because the benchmarks can change, the results can change. There is like a new big neural network coming out every single week. So commonly, like in the past, we used benchmarks like Glue and Blue for different parts, for the generative part and for encoders. Today, we have much more complicated systems for evaluation. I would not touch many of them today, but I would touch the problem of deployment. So the smaller model that we discussed today is Llama. If you want to get competitive results, you're going to use the 70 billion parameter version. Just accumulating the weights of the neural network would roughly give you 130 gigabytes worth of floating point numbers. 130 gigabytes is a lot. So if you take the DJX A100 servers, which used to be like about 300 grand per server, the starting price would include like GPUs with 40 gigabytes of HBM2 VRAM. So on 8 GPUs, this would be 320 gigabytes. And even with this much of VRAM and such expensive servers, you would not afford, you would not be able to have like multiple sequences per batch. So essentially, you would not be able to run too many concurrent queries on the same machine, which is absurd for like this cost. The players, the default one, of course, would be NVIDIA. They've been preparing the stack for way too long. They're the most mature player in the game. The contesters would be Intel, AMD, and ARM with CPU and GPU offerings. But then there are a number of specialized AI companies. With some of them we work, including GraphCore, SambaNova, and Cerebras. So like if everything is so expensive and the accuracy is fairly low, what can we do to improve it? Of course, as discussed previously, caching and external knowledge. For this, you need embeddings. For embeddings, the benchmark that everyone prefers is GLUE, General Language Understanding Evaluation. This is a multitask benchmark, so every column there is a separate objective. like various kinds of classification, sentiment analysis, all kinds of stuff. The problem that I'm most curious about is STS, which is the Semantic Textual Similarity Benchmark. It tells you how well the neural network performs when you compare one textual paragraph to another one. So for any kind of search-related workload, you're going to need to look into this specific column. So if the neural network has a high glue score, doesn't mean it's really good for search. The best encoders that I often use will, of course, include private ones, but also the public ones. BERT is the go-to original model popularized by Google. Distill BERT is much smaller version with just 60 million parameters, I guess, maybe 20. I haven't looked into it for a while. Mini-LM and E5 are also very interesting. So my general go-to first neural network that I use for encoders, for textual encoders, is generally E5. The second best option that I pick is Mini-LM. I was using it over this weekend as well. All those neural networks are tiny compared to LLMs. That's why they don't have L in their name, not large. They're very far from 10 billion parameters. They're generally below 1 billion. Some of them below 100 million, and if you're really lucky, you can train something in 10 million parameters. But the results most of the time would be garbage. I have very high hope for those kinds of models, and we've spent many years building them, but the results are not as shiny and glorious as with OpenAI. So the embeddings that you get vary in size and quality. Generally, like you are not losing anything by going from 32-bit floating point representations to 16-bit floating point representations. So do it the moment you can. You'll save at least half of your space. The next question is like, if you've reduced the size of every scalar value, can you reduce the size of the vector overall? Yes, you can do dimensionality reduction, but most likely you'll end up with distribution shifts, which is not a really good thing when you're working with already probabilistic system. It will be very hard to debug down the road from where the problem came out. So you probably want to start immediately with fairly small representations. So E5 and BERT models, they use 768 dimensional embeddings. If you need to go smaller, you can use 384 dimensional mini-LMs. And maybe like the last important piece is like how many languages the encoder was trained to understand. When you work with really large neural networks like OpenAI's ChatGPT, they kind of intrinsically get the multilingual capabilities because they're trained on a very large multilingual corpus. Small models do not generalize this well, so you have to be picky and understand what kind of model you are taking. If you go for E5, which I often do, you'll have the option to take the form in various sizes, like the small, the base, the large one. You can get the English one or the multilingual. There's no third option most of the time. There's oftentimes not even the second option available. So most of the neural networks are just trained for English data. Others are trained in multilingual setting, but English is always part of it. And rarely networks are specialized for one language. It generally either happens on very large markets like China and Russia. The last, maybe my most favorite category would be vector search. In here, you have like 3 categories of companies or projects. Engines, including the 3 open source ones by Meta called Face, Google's Scan, and Microsoft SPTAG. Face is the most popular one. It's the underpinning and the engine of a lot of vector search products. So this open source library may be like a better option if you want to build a vector search system, not using like the high level product, but going for the engine directly. If you still want to get like high-level functionality, the ease of use, online dashboards, and all those fancy things, and you don't care about scalability or costs, then of course there are specialized databases like Pinecone, Milvus, Qdrant, and VV8. The 3 last are open source, or generic databases like Elastic, Redis, Mongo, and Databricks. All of them are different. SQL, NoSQL, pick your poison. All of them support vector operations now. But I'm more curious about the engines. So engines, vector search engines, represent the application of a fairly interesting applied computer science problem, which is indexing high-dimensional vector spaces. And high-dimensional is a broad term. I guess maybe anything like beyond 1 is high, maybe beyond 2. So like those of you in the audience who are familiar with like old-school game engines have written KD trees, octa trees, and all kinds of other structures to index high-dimensional spaces. I used to do this stuff a lot. Then there are like super old-school approaches, a few hundred years old. that people generally don't classify as high-dimensional vector indexing structures. I still put them into this category. This would be space-filling curves. Some of you may be familiar with them through Postgres and other SQL-like databases, because when they started implementing GIS indexes, many of them implemented things such as Z-curves or more classic Hilbert curves as variants of space-filling curves that map two-dimensional points into one-dimensional space. They're quite fun. They don't scale well to high dimensions. The third one is locality-sensitive hashing, which applies only to dense vectors, but my favorite was just mentioned in the previous talk. It's the broad category of navigable small world graph algorithms, including their hierarchical variant published in 2016, I guess, shortly spelled HNSW. And the way HNSW indexes are benchmarked is through a combination of recall metrics and queries per second. Queries per second would be of two kinds, insertions and the search query itself. So in the process of insertions, you build the approximate index. The faster you can do, the better. Then the faster you can query it is also obviously better. But the question is, how much of accuracy do you lose like within this trade-off? Like going faster probably means you get worse results. The most famous library for benchmarking is called ANN benchmarks. It's a nice one, but I'm generally going for the bigger one, obviously big ANN benchmarks, which is a competition published around 1 billion vectors, and of course the objective is to search through them as fast as possible. When you start looking into those algorithms, I generally come from a very low level approach. But even if you use GNU utils and start benchmarking, you're gonna see that the metrics and like the bottlenecks of those algorithms obviously are similar to graph processing solutions. So you're gonna get a lot of branch mispredictions, and assuming a lot of search queries are memory bound and graph traversals are memory bound, you're gonna get a lot of CPU cycles wasted in the back end of the CPU pipeline. So stepping back for just a second, today feels like vector search is a crucial part of both AI applications, NoSQL databases, and SQL databases. I don't know where this all ends. I believe that there is some beauty in building open source, especially modular projects, when you can split the engine from the higher level implementation and then combine the way you prefer for your specific application. This is how it scales. And now we get to the part of shameless self-promotion and sharing what I do and finally introducing myself. So I run a project called Unum. I've been working on it for the last 8 years. I've been coding in C-like and low-level languages for most of the last 20 years. My background formally is astrophysics. For a number of years, I lived in Armenia and was running their C++ user group. And this year, finally, we started open sourcing a bunch of stuff that I was working on for the last couple of decades. This includes a lot of stuff related to AI that was not really interesting to people for most of this period, but now seems like they have their part in chain. So one of the projects is called uSearch. It's a vector search engine designed to scale well. So I see some elegance in being able to implement powerful solutions in very short code bases. And this will be true for every project I present here. So most of the projects, the core is just a couple thousand lines of code, mostly like in C99 or C++, 11, 17, or 20. A lot of those projects, because they're very tiny, they're very easy to embed into other products. And this was happening with a lot of those libraries, even though they're brand new. uSearch is now powering vector search within ClickHouse, a number of Postgres forks. It's used under the hood in large cloud providers. And it's kind of a replacement for Face, implementing just one indexing structure, HNSW, but doing it well. And because it's so tiny, it's easy to wrap into other programming languages and their runtimes. So the first 4 languages and the bindings I implemented within a day, together with the core itself. And it's probably 15th vector search engine in my career, including C++, obviously the implementation language, C99, Python, JavaScript, and Rust. But by now we have a lot more bindings and a broader ecosystem, which is really lovely. And one of the cool aspects of this thing is that HNSW is much more powerful than people think. it's not a vector search algorithm, it's a similarity search algorithm. As long as you can provide a similarity measure for your objects, you can use this as indexing structure. So say goodbye to inverted lists, one of my most hated data structures. I think search needs something more powerful, and I'm really glad that we have algorithms like this that we can implement and use like for something else, not just vector search, but even full text search. So now I'm in a process of designing the third major release of this library, and we're gonna get a lot of like full text search capabilities on top of the same data structure, even without AI, which is kind of fun. I love hacking stuff. The second thing is also related to the topic of search. It's called uform. You can get a lot of really good embeddings for textual applications, but there are not that many that are good with multimodal stuff. So OpenAI released CLIP, which stands for contrastive losses, at least the first few letters. And it's an approach to train multimodal transformers. So the idea is that, okay, we've known how to search text with text for many, many years, even without AI. Just like substring inclusions, and that's it. And then put BM25 on top of it and be done. But what about multimedia content? Yes, when we search images with images, we can use a unimodal transformer, like a vision transformer, to compare the embeddings of two images between each other and say if they're similar. But if you want to search images with text, text with images, images with images, and text with texts, all with a single neural network, you need to synchronize multiple transformers between each other. So that's what we did, and we've achieved it with a very, very small neural network, a lot smaller than OpenAI's CLIP and OpenClip, which is an open source reimplementation of this model. And assuming our somewhat international background, we wanted to make this neural network equally good with all kinds of languages, not just English. So we've prepared a lot of data sets to actually balance out English with other languages. So the neural network has seen equal amounts of English, Chinese, Russian, Hebrew, Armenian, Arabic, Spanish, German, and a bunch of other languages, which resulted in an unseen performance, especially on Hindi, which is hardly a low resource language with 600 million speakers, and Arabic with 300 million speakers or so. And the cool part is that because we love hardware, you can run this model not only on CPUs and GPUs, but also even the open source checkpoint on GraphCore IPUs. The next one is networking. So we've seen many, many times in our industry that sometimes very efficient single node solutions do not scale well or are not packaged properly. And the problem there is that we get all those networking libraries that are super slow. Every time they write into the socket, they perform a system call, and similarly, when they read from there. Luckily, the last few years, Linux kernel has seen a few nice developments with IO-Uring and user space approaches for IO. We've used them extensively in our database engines and networking libraries. We've also done some work on the opposite side, developing custom drivers, and those of you who are more interested in top percentile performance may want to build something with SPTK or DPTK, which are like full-blown user space drivers. The cool part is that even with IO-Uring, you can get most of this performance without actually having to suffer for too long. So starting up with IO-Uring is probably like a couple of days, even if you didn't have the experience. With SPTK or DPTK, you probably will not build something meaningful within the first month. So it's a stark difference. The interesting part here is that when the kernel 5.19 of Linux was released previous year and got available in all kinds of different distributions, including Ubuntu, I've hacked together a system that uses the new ability to allocate file descriptors for sockets directly from IO-Uring's managed pool. And this way you can avoid a bunch of different latencies. As a result, you can wrap it up into a library for fast serving of search results, for example. So when we've built uform, this model, on a service that I've just mentioned, we could achieve 300,000 inferences per second. So of course, you're not getting the same results as ChatGPT, but for search, you don't need the same level of accuracy and generation. You need throughput. But Fast API and most other libraries, including gRPC, they only scale to thousands of operations per second, at best tens of thousands. And with this library, with proper kernel bypass and a clean C99 implementation, you can get to over 200,000 queries per second on a single server core. And then, not stopping there, I also designed a bunch of libraries in the last years to work with those large data sets more efficiently. Those are tiny tools. One of them is called Stringzilla. I kind of republished it this summer, just a couple of months ago. It's a library that uses seamed intrinsics. For you not familiar with the topic, it's a way of doing intra-core parallelism, in a sense that a single core would be able to do multiple operations in a single CPU cycle. Processing vectors like this is fairly easy. Processing strings of variable length is a bit harder. But working with data sets like Common Crawl, which is by itself already 300 terabytes, and doing it on every one of your machines and not on a cluster that is like an entire data center in size is pretty hard. And this library has saved me a lot of money and many, many weeks of data engineering work. So I'm happy to share it with others. And we are now adding JavaScript bindings. And the library to which I've just added JavaScript bindings tonight at 6 a.m. is SimSimd. So this library I've also just released a few weeks ago as a separate thing. So this is one of those things that powers vector similarity within usearch. One of the reasons we can do vector search so fast is not only because we avoid memory allocations aggressively and do not do many mutexes and logs and scale perfectly like to hundreds of cores in every single machine, but also the fact that we can compare vectors quite efficiently. For this, there's like a lot of hardware capabilities that have been exposed in the last couple of years, and most libraries, even the ones that are considered fairly low level, like BLAS, basic linear algebra subroutine standard, they're falling far behind in terms of their support for those like assembly instructions. So there's OpenBLAS, which is like further behind. Of course, companies like Intel provide MKL, like Math Kernel Library, for their own backend, which is amazing. But if you want to have something that works fast, even like on smaller vector sets, not just huge matrices, NumPy and underlying BLAS is not the best option. So by exposing this library as a separate thing, you can replace your SciPy calls to distance metrics, especially the spatial ones, with a variance that accelerated not just with AVX2, but also with AVX512 FP16. This is like the newest instruction subset only available on this year's CPUs, mostly sub-5 Rapids. And also on ARM-Neon and SVE. SVE stands for Scalable Vector Extensions. They are only available on modern Ampere Ultra chips and AWS Graviton 3. But if you are already paying for this hardware and you are using the most recent chips, then it would be sad not to use like 100x performance improvement that you could have been getting by using the right assembly instructions down there. So with this, I want to wrap it up and want to leave you with a few libraries that I want to encourage you to use. Of course, some of them are mine, but some of them are also like broader libraries available to everyone under Apache 2 license. And I use them every day. I just participated in a hackathon over this weekend for fun, and we won the third prize just because we were able to combine those tools in a nice way. So I'm encouraging every one of you to try them as well and contribute. Thank you. Any questions? Please. Yeah, sure. So there's not much difference. I also talked a lot about indexing. It's just a question of the layer of abstractions that you prefer for your solution. So you can go for a full-blown product that has a lot of functionality on top of it, and most likely you'll lose not just one, but a few orders of magnitude of scalability. And the question is like, does your application need it? Do you want to like index 1,000 vectors? If so, you probably don't even need an index. You just do like full scan. 1,000, 1,000,000. Okay, at 1,000,000, you start thinking about latency. In my case, I generally aim for billions per node. So at that level, you cannot afford like any one of the existing solutions, so you have to build your own. And sometimes you want to share it with everyone else to use in their applications. So some databases have been now integrating our solution, which means you may be using it down the road without realizing it, and you will still get a lot of the functionality, but you may not need the whole like throughput thing. Hope this answers. Any more questions? Yes. Okay, so I think I haven't explicitly said it, and I don't think so. Like almost everyone in the industry thinks that just scaling a transformer is like the adequate strategy every time like you want to increase accuracy on whatever benchmark. First, I don't agree with that. I'm not sure if I've mentioned during the talk. But then there are also a few really good examples of how you can achieve very high accuracy in your generative model, such as LLM, by tuning your data set. And this year we had a paper called Tiny Stories, which showcases how you can build like a very, very small data set, sometimes synthetically, so that you train a very small model, and it would still produce texts that are somewhat indistinguishable from human written text, but only within like a specific domain. So this is definitely possible, but requires more research and is not very broadly applicable across every domain. More questions? Yes? So there are a number of benchmarks, including STS, on which it performs well. It's fairly high dimensional, more like maybe too much. But when I worked with it in various domains, it almost kind of never degraded. And even on like highly technical subjects, and moreover, it allowed me to do a lot of different kinds of quantization and downcasting. So one of the things that I haven't touched in this talk is quantization, which is a hybrid technique that you can use with any proper vector search approach, kind of reducing the size of your vectors, either by reducing the number of dimensions or the size of every scalar value. So common approach would be to downcast to float 16, either IEEE standard or brain float 16 with like large exponent. Or you can go further. You can downcast to int8 representations. So you scale up your vectors that are generally conceived of values from 0 to 1 to, let's say, a broader interval, let's say 0 to 100. And then you compute the similarities between those integer vectors, which is super hardware friendly. You can run it on anything like RISC-V chips, Raspberry Pis of any kind. It just works seamlessly and super high performant. And you can also accelerate it with steamed assembly quite easily. You can go further. You can do int4. And the question is like, how much of like the accuracy you lose by doing all those quantizations? And with some models that are trained better or have more expressive capability, or maybe trained with quantization-aware training techniques, that's the technical term for it, you may have like more headroom in terms of like your quantization experiments. But of course, mini LLMs are also worth considering. Any more questions?
Question. Yeah, so you mentioned the different hardwares on USearch and Uform. I'm interested in, have you done research on the FPGA side? Has that been fruitful or not? Is that something you're looking into or not?
Yeah, sure. So like, it just so happened that we are surrounded by a lot of FPGA companies and a lot of friends there. FPGAs are of course attractive, but to be honest, like for them, it might be hard to compete like in classic AI workloads. You're better off taping off an ASIC for that. We mostly work like on the CPU side, GPU side, and also like understanding how external memory works, like SSDs and PMEM, and like those are of course hybrid structures with non-flash and FPGA on top and DDR and like all that stuff. So the problems that those libraries solve are very different. They have different hardware bounds. So when you solve search, you're memory bound, you're IO bound. So you want fast memory. You want like DDR5, you want HBM. That's why it's actually like so beneficial to be optimized for the newest hardware like Sapphire Rapids and Graviton, because they support DDR5 and the memory bandwidth is double the previous generation. With Uform, you're doing inference. And if you want maximum throughput, you go to GPUs. If you want to do CPU inference or like minimum latency, you go for CPU inference. And in there, like we've done some interesting work. We haven't announced it publicly yet, but I guess it's a cool occasion, so why not? We got the inference time of Uform models down to 1.3 milliseconds on a CPU, which is like an unseen number in the industry. And this is mostly due to Intel's AMX instructions, which are tiled matrix multiplications. And I will be working on integrating those assembly instructions in SimSim and USearch down the road, which is probably the first open source library out there to use all of that functionality. So hopefully this answers your question. Any more? That's a really good question. So for LLMs and generative models, there is like this paper called Scaling Laws of Large Language Models, but those this is for generative models. And encodings and embeddings, those are not generative models. For them, I don't know if there's like a paper like this that defines like a proper standard or methodology for how you scale it. But we have an intuition because like we've done, like we do over a few hundred experiments every year on the same topic. What you see on this slide is the model cards on Hugging Face for E5 models. The first and the second one are base and multilingual variants. If you look down, you'll see the number of parameters. The single language variant is 109 million parameters and multilingual is 278. Most of the difference is in the bottom layer, which is responsible for mapping the tokens into specific small-ish embeddings for every single token. And the wider is your vocabulary, and as you go to more languages, your vocabulary becomes wider. The bigger is the first layer, the beefier it is. So most of your neural network is kind of shifting down. There are approaches to circumvent this. They're called LoRa and the variations of this acronym. But to dive deeper, you'd probably need like to do a proper research and understand how this would affect your specific application. And don't try to go to all languages at once. We first went with UForm from one language to about 8 or 10, and it took a lot of time. And going to 21 required a lot of experimentation and wasted GPU hours. Any more questions? Okay, thank you very much. It was a pleasure.